Yeah, actually.
All right, welcome everyone. So as a reminder, homework 1 is due on Monday, and then I will have homework 2 covering material starting today, ready for you by Monday to work on for the following week. So today we're talking about distributions related to the normal distribution. So in other words, if we take a sample from a normal distribution and then compute various statistics about it, what can we say about the distribution of those statistics? All right, so to get us started, we have theorem 6.4, which you saw briefly last semester, and 7.2. And when you combine these, they say, we'll let y sub I be a normal random variable with mean, mu, and standard deviation, sigma. So we have a sample of independent y sub i's from a normal distribution. Then, as you know, if you take the y value minus the mean and divide by the standard deviation, you get independent standard normal random variables. So this is the same thing that we've been doing whenever we use the normal probability table to compute probabilities for a normal distribution. So we start by converting y sub I into a standard normal. And then this is just saying, say we start with the y sub i's being independent. If all we do to them is subtract the mean and divide by the standard deviation, they stay independent. So this part 1 is familiar to us. Then part 2, this is theorem 7.2, says that if we take these standard normal random variables that we created and square them and take the sum, we get a new random variable that has a chi-squared distribution with n degrees of freedom. And the proof of this uses moment generating functions, our old standby. And you can check out section 6.5 if you want to see that proof. All right, so the chi-squared distribution we saw yesterday in lab is this right-skewed distribution that models values of y between 0 and infinity. It's actually a special case of the gamma distribution. So it has a mean of v or nu, whatever its degrees of freedom are. And its variance is 2 times its degrees of freedom. And so here you can see the R code to work with a chi-squared degrees of freedom, chi-squared distribution function, which you've already worked with. It's whatever the prefix letter is that you're interested in, and then CHISQ for chi-squared. So here we're using the R prefix to generate random numbers, So here we're generating 10,000 random numbers from a chi-squared distribution with v degrees of freedom. Questions so far? All right. So we're going to use that, theorem 7.2, to help us prove theorem 7.3. So here we're letting the y sub i's be independent and identically distributed normal random variables with mean, mu, and standard deviation sigma. So we can again think of the y sub i's as being a random sample from a normal distribution. And we'll let s squared be the sample variance. That has the usual formula, s squared equals 1 over n minus 1, where n is the sample size, times the sum of y sub I minus the sample mean y bar quantity squared. All right, so if the y sub i's and s are defined like that, then the result you saw in lab yesterday was that n minus 1 times s squared over sigma squared has a chi-squared distribution with n minus 1 degrees of freedom. So here, S is the standard deviation of the sample. So S squared is the variance of the sample. And sigma is the theoretical standard deviation of the whole population, or the underlying distribution that we use to generate the y sub i's. Additionally, the sample mean y bar is independent of the sample variance s squared. All right. So we're going to go through the proof of this just for the case where the sample size is 2. So we're going to let y1 and y2 be independent and identically distributed normal random variables with mean, mu, standard deviation sigma. All right. Coming up on homework 2, you'll show that when n is 2, then the sample variance s squared is equivalent to y1 minus y2 quantity squared over 2. So then our statistic that we're interested in, this n minus 1 s squared over sigma squared, well, we're working with n equal to 2, so n minus 1 just becomes 1. And then we can replace the s squared by y1 minus y2 quantity squared over 2. So we get y1 minus y2 squared over 2 times sigma squared. And then we can rewrite that so the whole fraction is squared. So we have y1 minus y2 over the square root of 2 sigma squared, all squared. And why we're rewriting it that way will become apparent in a moment. Questions so far? All right. So now, y1 minus y2 is a linear combination of independent normal random variables. So it's also normal. So that's a consequence of theorem 6.3. All right, so we know it's a normal random variable. Try finding its mean. So the mean of y1 minus y2. So recalling that y1 and y2 each had a mean of mu and a standard deviation of sigma. The mean of y1 minus y2. So in other words, the expected value of y1 minus y2. And then the y-sides were identically distributed, so they actually have the same. Okay.
It's a different
Yep, so because the y sub i's were IID, that means independent and identically distributed. That means that they have the same mean mu and the same standard deviation sigma.
Does that mean that the same distribution, or is there something different?
So they're different random variables, but they're drawn from the same distribution.
Oh.
So if you were doing this in R, it would be like R norm 2 comma mu comma sigma. So you might get different values. All right. So what is the mean or expected value of y1 minus y2 going to be? 0. Very good. So by the linearity of expected value, we can split it up across its subtraction. So we get the mean of y1 minus the mean of y2, but because they're identically distributed, they have the same mean. So y1 minus y2 has a mean of 0. All right. How about the standard deviation or the variance? So try using, I would recommend the table method to find the variance of y1 minus y2. Give me the sum of that. That's it. Shouldn't be zero because it's end up. So what did you go through? Actually, U is the variance. And what is the variance for conjugate sigma? All right. So our variance covariance table looks like this. So the variance of y1 is sigma squared because the standard deviation was sigma. Y2 has the exact same standard deviation, so its variance is also sigma squared. And the y sub i's were independent, so the covariance is 0. So that's our original table. Then we multiply by the coefficients. So we implicitly have a 1 times y1 and a -1 times y2. So we get 1 times sigma squared plus -1 times -1 times sigma squared. So that's sigma squared plus sigma squared. So we get a variance for y1 minus y2 of 2 times sigma squared. Questions about this? All right, so y1 minus y2 is normal with a mean of 0 and a variance of 2 times sigma squared. Or in other words, a standard deviation of the square root of 2 times sigma squared. Well, that means that if we take y1 minus y2 minus its mean and then divide by its standard deviation, we get a standard normal random variable. So that's theorem 6.4. So now you might see why we put our target statistic, our n-1 s squared over sigma squared, why we wrote it in that format that involved a y1 minus y2 over square root of 2 sigma squared. It's because by theorem 7.2, we talked about at the start of class, this thing, y1 minus y2 over the square root of 2 sigma squared, all that squared, that's a standard normal random variable squared. So that means it's a chi-squared random variable with 1 degree of freedom. So therefore, when n is equal to 2, then our target statistic that we started with, n minus 1 times s squared over sigma squared, really does have a chi-squared distribution with n minus 1 degrees of freedom. Questions about this? All right. We can also sketch the proof that y bar and s squared are independent. So the sample mean and the sample variance. So to do this, we're going to start by defining 2 new random variables. We'll let u1 be y1 plus y2 over sigma, and u2 equal to y1 minus y2 over sigma. So you can use the bivariate method of transformations to find the joint density function of u1 and u2. So for example, when y1 and y2 are standard normal, you end up with this density function here. So e to the negative u1 squared over 4 over square root of 2 square root of 2 pi, e to the negative u2 squared over 4 over square root of 2 square root of 2 pi. And if you want to see this proof, that's example 6.13 in your book. Anybody recognize what kind of density function this is? Isaac, got an idea? No, it's not beta because the range of possible values for the u's is between negative infinity and infinity. And if it were beta, it would just be from 0 to 1. Naya?
Is it normal?
Yeah, this is a bivariate normal density function. So you can sort of see that if you just ignore u2 and just focus on this first one. We have e to the negative variable squared over something. That's our sort of fundamental unit of what the PDF of a normal distribution looks like. And then the constants end up being whatever they need to be to get the integral to equal 1. So it turns out that this is a bivariate normal distribution, specifically with correlation equal to 0. if the correlation were non-zero, then there'd be like an extra factor in the middle here that involved both U1 and U2 and the correlation coefficient. All right, so U1 and U2 are bivariate normal with correlation equal to 0. And we know that if two random variables are independent, then they have correlation equal to 0. And usually you can't go the other way. But in the specific case of a bivariate normal distribution, if the correlation is 0, then the random variables are also independent. So in the specific case of bivariate normal, that implication goes both ways. Correlation independent implies correlation equal to 0, and for bivariate normal, correlation equal to 0 implies independent. All right, so U1 and U2 are independent. And now we can write Y bar as 1/2 sigma U1. So that's a function of U1 by itself. And we can write S squared as 1/2 times sigma U2 quantity squared. That's a function of U2 by itself. So we showed that U1 and U2 are independent. And now we've showed that Y bar is a function of just one of them, and S squared is a function of just the other of them. So that shows us that Y bar and S squared are also independent. Questions about this? All right. So let's take a look at an example of when we might want to use this random variable. So take a moment to read problem 1 and think about how this new result that we just proved about the distribution of n-1 s squared over sigma squared might be useful. And Vivian, this is problem 1 on distributions based on the normal distribution. right, what probability are we trying to find here? Okay,
The standard deviation is greater than 0.04.
great. So probability that the sample standard deviation S is greater than 0.04. So our strategy here, and for a lot of problems that we're going to be doing sort of today and into next week, is try to do the same thing to both sides of the inequality inside the parentheses of the probability. So we're keeping the inequality the same until we get a variable on one side of the inequality that has some known distribution. And in this case, because our probability question is about the standard deviation of one sample, a good goal is to get it to look like n-1 times s squared over sigma squared. Because really, like the n is going to be a constant, and sigma squared is the standard deviation of the population, 0.04869. That's a constant as well, as far as this problem is concerned. So we want to sort of match up the random variable s with the random variable we're trying to find the probability of. All right, so why don't you try that? Try rearranging the portion inside the probability so it has the format of n-1 s squared over sigma squared. My recommendation as you're doing this is to try to keep one side of the inequality all in terms of the random variable and then the symbols representing known constants. So sigma and n, and try to keep the other side of the inequality just in terms of actual numbers. That'll help you sort of communicate and organize your results. All right, so here we started with the probability that S was greater than 0.04. We squared both sides of that inequality, then multiplied both sides of the inequality by n-1 over sigma squared. So on the left-hand side, we wrote that in terms of symbols, and on the right-hand side, we wrote it as 15 over the square of sigma, which we were given in the problem. So then we can simplify that right-hand side. It works out to about 10.1235. Questions about this part? All right, so this left-hand side of the inequality, n minus s squared, or n-1 s squared over sigma squared, that is a statistic. It's a formula based on a sample, so based on the sample standard deviation and known constants, n and sigma. So because it's a statistic, it's a random variable, so it has a distribution. What distribution does it have? Chi-squared, with how many degrees of freedom? 15, yeah, n-1, which in this case is 15. So our original question of the probability that the sample standard deviation was greater than 0.04 is equivalent to the probability that our new random variable x is greater than 10.1235, where x has a chi-squared distribution with 15 degrees of freedom. So if we want to compute that probability in R, what prefix are we going to use? No? P is going to give us the probability of being less than something. Here we want the probability of being greater than something, so we could do 1 minus P. We're working with a chi-squared distribution, so the root of that is going to be CHISQ. And then we want the probability of being greater than 10.1235. With our degrees of freedom equal to 15. So that probability is 0.811. questions about this? All right. So this is great and all, but what about random variables based on two different samples? So here we have definition 7.3. We're going to let W1 and W2 be independent chi-squared random variables with degrees of freedom V1 and V2. Then the random variable that's equal to W1 over its degrees of freedom divided by W2 over its degrees of freedom. By definition, we call that an F distribution with two different degrees of freedom to describe its shape. So V1 is the numerator degrees of freedom and V2 is the denominator degrees of freedom. So here's what the F distribution looks like. Like the chi-squared distribution, it's right skewed, and it's defined for values of y between 0 and infinity. Its expected value, or its mean, is, let me double check that. I think there might be a V1 in there. Nope, yep, it is V2. So its expected value is V2 over V2 minus 2, assuming that its denominator degrees of freedom V2 is greater than 2. If its denominator degrees of freedom is 2 or less, then the expected value is not defined. The variance of the F distribution is finite as long as V2 is greater than 4, but it has a pretty complicated formula. So typically we're not going to worry about it in this class. Typically we'll compute it computationally, empirically using R if we need it. And then to work with the F distribution in R, it's going to be using the same 4 prefixes as we've seen for other distributions, and its stem is just F. So if we want to generate 10,000 random numbers from an F distribution, we just use the function RF of 10,000, comma, numerator degrees of freedom, comma, denominator degrees of freedom. Questions about this? All right. So this is a scenario where we might be interested in this. This is problem 2. So a pharmaceutical company has developed a new way to measure cholesterol, which is cheaper than the standard method. Both measurements produce measurements which are normally distributed around the true cholesterol level, but critics say the new method is less precise than the standard method. Suppose that cholesterol was measured on the same blood sample 10 times using the new method and 6 times using the standard method. And the sample variances were S squared equal to 8 for the new method and S squared equal to 4 for the old method. And we want to know, is this evidence that the new method is less precise? Take a moment to think about this situation and think about how the F distribution might help us with it. So what did we do previously when we wanted to test whether something was evidence of a particular claim? Okay. Yeah, we assumed that the claim was false, or assume that there's sort of the status quo is going on. Assume that there's really no change or no difference between the two methods. So assume both methods are equally precise. So in this case, we'll assume that the true population variance, sigma squared, is the same for both of the methods. And then find the probability of getting a result at least as extreme as what we got in this data. So that's what we'll be doing using the F distribution on Monday. I'll see you then.